Module 1 Overview of WAN Connections. Companies that have multiple offices need a cost-effective, efficient means to exchange data between those offices. Many companies have created intranets or extranets, which enable users at different locations to view, upload, and download information. However, intranets and extranets are only a partial solution to the problem because the sharing of data is limited to what can be posted on the intranet or extranet. Each office must maintain its own database, and users cannot access data stored at other locations. For example, the accounting department at each office must have a separate database which cannot be shared over an intranet. Security is also an issue because the intranet must be connected to the internet in order to serve multiple locations. The various offices connected through the intranet can be protected by firewalls, but firewalls are not impervious to attacks. For many companies, a wide area network, or WAN, is a better and more cost-effective solution for connecting multiple branch offices to a main office. A WAN allows companies to exchange all types of information, including voice and data. Combining voice and data traffic can reduce operating expenses for many companies. This course focuses on WAN connections created using public carrier networks. Businesses, organizations, and government entities use public carrier networks to create WAN connections for three primary reasons. Using a public carrier network infrastructure is almost always more cost-effective than using privately owned infrastructure. Public carrier networks allow many subscribers to share the costs of installing, managing, and maintaining the infrastructure required to create WAN connections. Using privately owned infrastructures to create long-distance and international WAN connections is impractical, sometimes even impossible, and cost-prohibitive. WAN connections that use a privately owned infrastructure are generally limited to relatively short distances, and installing them is beyond the capacity of all but the largest organizations. WAN connections created through public carrier networks are substantially similar to WAN connections created using privately owned infrastructure in terms of security and performance. Public carrier networks also provide levels of reliability and redundancy that a privately owned infrastructure typically cannot provide. WAN routers connect the local area networks, or LANs, at each location, identify the traffic address to another LAN, and route the traffic to the next hop. As explained throughout this course, WAN routers support a variety of WAN connection types, including dedicated T, E, and J carrier lines, Integrated Services Digital Network, or ISDN, Digital Subscriber Line, or DSL. In the most general sense, a WAN is a geographically dispersed telecommunications network. For the purposes of this course, however, a WAN is defined as a network created to connect two or more LANs. WAN connections can connect LANs located in the same city or around the world. As the slide shows, a public carrier network is commonly used to create WAN connections between LANs in different parts of the world. Public carrier networks include the Public Switched Telephone Network, or PSTN, which serves the United States and Canada, and Public Telephone and Telegraph, or PTT companies, which serve Mexico, Europe, Asia, South America, and other parts of the world. All WAN connections consist of three basic elements: the physical transmission media, electrical signaling specifications for generating, transmitting, and receiving signals through various transmission media, data link layer protocols that provide logical flow control for moving data between peers in the WAN. Peers are the devices at either end of a WAN connection. As the slide shows, physical transmission media and electrical specifications are part of the physical layer, Layer 1, of the Open Systems Interconnection, or OSI model, and data link layer protocols are part of the data link layer, which is Layer 2. This module focuses on the physical transmission media, the electrical signaling specifications, and the related OSI Layer 1 technologies that are used to create WAN connections through public carrier networks. Data link layer protocols are explained in detail in Module 2. The first basic element of a WAN connection is the physical transmission medium. The most common physical transmission medium used in public carrier networks is twisted pair copper wire, originally installed for plain old telephone service or POTS connections. Twisted pair is currently used in the last mile of 90% of all WAN connections. Other physical transmission media include coaxial copper cable, fiber optic cable, and the Earth's atmosphere, which carries signals by such means as infrared and microwave transmissions. The physical transmission media are a large part of what is commonly called infrastructure. Infrastructure also includes telecommunications switching and routing equipment. WAN connections can be created using public carrier network infrastructure, privately owned infrastructure, or a combination of the two. As the slide shows, 3 types of circuits are used to create WAN connections through public carrier networks: dedicated circuits, permanent virtual circuits, switched virtual circuits. Dedicated circuits are permanent circuits dedicated to a single subscriber. The connection is always active. The subscriber purchases dedicated time slots or channels that provide a specific amount of bandwidth that is always available for the subscriber to use. The channels in a dedicated circuit are created using time division multiplexing or TDM, which is discussed later in this module. In addition to providing guaranteed bandwidth at all times, dedicated circuits provide the most secure and reliable WAN connections available. They are used to create the following point-to-point WAN connections: carrier lines, which are explained later in this module and in Module 3. DSL connections, which are explained in Module 5. Permanent virtual circuits, or PVCs, are also permanent circuits dedicated to a single subscriber. The connection is always active. However, because multiple virtual circuits share a physical circuit, there is no guarantee that any specific amount of bandwidth will be available at any specific time. Sometimes there may not be any bandwidth available on the physical circuit because the physical circuit is saturated. When the physical circuit is saturated, the traffic is temporarily stored at a switching point. When bandwidth becomes available, the stored traffic is forwarded to its destination. This process is referred to as store and forward processing or packet switching, which is the same processing method used on LANs. PVCs provide an average bandwidth guarantee using statistical multiplexing or STM, which underlies packet switching technology. Because PVCs are more cost-effective for the public carrier, they are usually less expensive for the subscriber than dedicated circuits. PVCs are commonly used for frame relay, which is explained in detail in Module 6. Switched virtual circuits, or SVCs, are identical to PVCs in all respects, except that they are temporary physical circuits. SVCs are activated when a subscriber initiates a connection to transmit data. When all data has been transmitted, the connection is deactivated, and the physical circuit resources are made available to other subscribers. SVCs are used to create dial-up WAN connections, including ISDN WAN connections, which are explained in Module 4. In the United States and Canada, most WAN connections are created through the PSTN. As the slide shows, the PSTN consists of local exchange carriers, or LECs, and inter-exchange carriers, or IXCs. LECs are also referred to as telcos. LECs operate the infrastructure that provides access to the PSTN in a limited geographic area. The area served by a LEC is referred to as a Local Access and Transport Area, or LATA. LECs include incumbent local exchange carriers, or ILECs, and competitive local exchange carriers, or CLECs. ILECs are the regional bell operating companies, or RBOCs, that provide service in a specific LATA. For example, SBC is the current ILEC in California. ILECs were created in 1983 when the U.S. government deregulated the telecommunications industry and mandated the breakup of AT&T. Deregulation also led to the creation of CLECs, which provide the same services as ILECs and compete with ILECs in specific geographic areas. For example, COVAD Communications is a CLEC that competes with SBC in California. IXCs aggregate voice and data traffic from numerous LECs. They operate the infrastructure that connects LATAs to the inter-LATAs that move traffic throughout the United States and Canada. AT&T, Sprint, and MCI are all IXCs based in the United States. IXCs are commonly referred to as long-distance carriers. IXCs also provide the infrastructure that enables PSTN subscribers to create WAN connections to PTT networks in Europe, Asia, South America, and other parts of the world. In most countries outside of the United States and Canada, the public telephone network is owned and operated by government-owned monopolies called PTTs. As the figure shows, a PTT operates the entire telecommunications infrastructure within a country's borders. For example, British Telecom, or BT, provides border-to-border service in the United Kingdom, while Deutsche Telekom, or DTAG, provides this service in Germany. PTTs provide both the local access and long-distance transport infrastructure needed to create WAN connections through the public carrier network. As the figure shows, carrier interconnects link individual PTTs to provide an international public carrier system. The connection between a subscriber's premises and the public carrier's nearest central office, or CO, is referred to as the local loop. The local loop includes the entire telecommunications infrastructure, such as repeaters, switches, cable, and connectors, required to connect a subscriber's premises to the CO. A line of demarcation, or demarc, separates a subscriber's wiring and equipment from that of the public carrier. Each party owns, operates, and maintains the wiring and equipment on its side of the demarc. Public carrier networks were originally designed to carry analog voice calls. Therefore, copper wire is the most common physical transmission medium used on the local loop. Because of the limits in the signal carrying capacity of a copper wire, local loops that use copper wire are the slowest, least capable component of a WAN connection. Public carriers are beginning to install coaxial and fiber optic cable in local loops to meet ever-increasing bandwidth demands. Local loop connection types include carrier lines, which are described in Module 3. Local loop connection types also include ISDN and DSL. ISDN and DSL are digital technologies designed to maximize the limited capabilities of existing local loop copper wiring. ISDN and DSL are discussed briefly in the next two sections. ISDN provides integrated voice and data services by means of a fully digital local loop. An ISDN connection requires Category 3 or Cat3 or higher twisted pair and is delivered by means of an SVC. ISDN is a local loop-only technology. When ISDN traffic reaches the public carrier's nearest CO, it is converted for transport through existing public carrier infrastructure. ISDN is available in two levels of service: Basic Rate Interface, or BRI, and Primary Rate Interface, or PRI. BRI service provides 128 kilobits per second of bandwidth. PRI service provides 1.544 megabits per second in total bandwidth in T-carrier systems and 2.048 megabits per second in total bandwidth in E-carrier systems. ISDN is discussed in depth in Module 4. DSL is a digital service that exists only in the local loop. DSL provides a digital connection between the subscriber and the public carrier's CO. Like ISDN, DSL requires Cat3 or higher twisted pair wiring. Unlike ISDN, DSL uses PVCs, so DSL connections are always active. A DSL modem or WAN router connects the subscriber's premises to the public carrier network. Different types of DSL are available. Each public carrier determines the types of DSL that are available in a local service area. DSL types include asymmetric DSL or ADSL, high bitrate DSL or HDSL, symmetric DSL or SDSL, and very high bitrate DSL or VDSL. DSL is discussed in depth in Module 5. Cat3 and Cat5 unshielded twisted pair or UTP are the most common types of copper wire used in the local loop. In some applications where signal interference is an issue, shielded twisted pair or STP is used. In some areas, including parts of the United Kingdom and the Netherlands, a pair of coaxial cables is used instead of twisted pair to complete local loop connections. Other transmission media can be used to complete local loops if transmission speed is a primary consideration. For example, fiber optic cable and coaxial cable are both used to create T3 and E3 WAN connections, as discussed in Module 3. An electrical specification defines a set of communication parameters or rules that determine the transmission speed through a WAN connection. When engineers create an electrical specification, their objective is to find the best way to reliably transport traffic as rapidly as possible through a given transmission media. The electrical specifications used for public carrier networks are based on cooperative standards developed by the American National Standards Institute, or ANSI, the International Standards Organization, or ISO, the Conference of European Postal and Telecommunications, or CEPT, the Telecommunications Standardization Sector of the International Telecommunication Union, or ITUT, and the ITUT's predecessor, the Consultative Committee for International Telegraph and Telephone, or the CCITT. Electrical specifications enable both synchronous and asynchronous communications over a WAN connection. Synchronous communications use a clock signal to precisely coordinate signal transport through the transmission media. Asynchronous communications use start and stop bits rather than a clock to coordinate signals. The remainder of this module focuses on the synchronous electrical specifications and related technologies that define the basic unit of bandwidth, the digital signal 0 or DS0 channel used in copper-based public carrier networks. DS0 is a digital channel operating at 64 kilobits per second, the amount of bandwidth required to transmit a single analog voice call through a digital telecommunications network. Based on the ANSI T1.107 specification, DS0 was originally created in the mid-1960s by Bell Laboratories to transport voice traffic over T-carrier systems. PTT subsequently adopted a modified version of ANSI T1.107, the ITUT G.703 specification, which is the basis of European and international E-carrier systems. J-carrier systems are also based on a modified version of T1.107 and are similar to T-carrier systems. DS0 is the fundamental unit of bandwidth, the fundamental channel, in all copper-based T, E, and J-carrier systems. In E-carrier systems, DS0 is called E0, and in J-carrier systems, it is called J0. However, the basic signal is virtually identical in all three carrier systems. DS0, E0, and J0 channels all use a process called pulse code modulation, or PCM, to convert analog or voice signals into digital signals. PCM is the basis of a standard DS0, E0, and J0 channel. PCM converts a continuously variable analog signal, such as a voice telephone call, into a stream of digital bits. As the slide shows, the PCM sampling process creates a digital signal that represents the original analog waveform. The analog signal is converted or modulated into a digital signal that is sent over the WAN connection. On the receiving side, the digital signal is demodulated or converted back to an analog signal that closely approximates the original analog waveform. In the PCM sampling process, the analog signal is sampled 8,000 times per second. Each sample is converted into an 8-bit binary code that represents the voltage of the analog waveform at the time the sample was taken. Thus, the PCM process is the mathematical basis for the bandwidth required for a standard DS0, E0, or J0 channel. 8 bits per sample times 8,000 samples per second equals 64 kilobits per second. As the slide shows, TDM creates a high bandwidth channel by combining or multiplexing multiple DS0 signals into a larger, more complex signal. Each DS0 receives an equal time slice within the complex signal in a rotating repeating sequence, and thus receives an equal amount of bandwidth. On the receiving end, TDM is used to recover the original DS0 signals through a reverse process called demultiplexing. T-carrier and J-carrier systems use TDM to provision 24 DS0 channels for a T1 or J1 WAN connection. E-carrier systems use TDM to provision 32 DS0 channels for an E1 WAN connection. TDM is also used to provision larger channels that use T1, J1, or E1 channels as base multiples, as described in the next section. Digital signaling hierarchies define the signaling multiplexing used in each type of physical carrier and determine the transmission speed for each carrier. Digital signaling hierarchies use small bandwidth channels as base multiples for creating larger bandwidth channels or carrier signals in a carrier system. DS0, E0, and J0 channels serve as the base multiples for creating T1, E1, and J1 carrier signals. T1, E1, and J1 in turn serve as the base multiples for creating the more complex, higher bandwidth carrier signals used in T2, E2, J2, and higher carrier systems. T, E, and J carrier systems use similar, but not identical, digital signaling hierarchies. T carrier systems use digital signal X, or DSX. E carrier systems use the SEPT digital signal hierarchy, and J carrier systems use the Japanese signal hierarchy. These signaling hierarchies are described in the following sections. DSX is the digital signal hierarchy that defines the signal multiplexing used in T carrier systems. As the figure shows, DSX specifies that 24 DS0s are multiplexed to create the DS1 carrier signal used in a T1 carrier. A T1 carrier provides a total transmission rate of 1.544 megabits per second. 24 times 64 kilobits per second equals 1,536 kilobits per second, plus 8 kilobits per second for framing bits and timing signal synchronization. Similarly, DSX specifies the following. 4 DS1 signals are multiplexed to create the DS2 signal used in T2 carriers. T2 carriers provide a total transmission rate of 6.312 megabits per second. 28 DS1 signals are multiplexed to create the DS3 signal used in T3 carriers. T3 carriers provide a total transmission rate of 44.736 megabits per second. 168 DS1 signals are multiplexed to create the DS4 signal used in T4 carriers. T4 carriers provide a total transmission rate of 274.176 megabits per second. 336 DS1 signals are multiplexed together to create the DS5 signal used in T5 carriers. T5 carriers provide a total transmission rate of 560.160 megabits per second. As the slide shows, DSX specifies the physical carriers used at each level in the hierarchy. DSX does not define the physical carrier. ANSI T1.107 defines the physical components of T-carrier systems. When combined, the physical carrier and the DSX hierarchy specify a usable physical layer for each type of carrier in a T-carrier system. DSX defines digital signal designators, or DSDs, the signaling methods used to create the carrier signals at each level of the hierarchy. DSX also defines DSX interfaces, the physical connections or pinouts, and the signaling logic, send timing, receive timing, send data, and receive data necessary for connected devices to communicate. Like the DSX digital signal hierarchy used in T-carrier systems, the SEPT digital signal hierarchy defines the signal multiplexing used to create the signals carried in each E carrier. Unlike DSX, SEPT DSDs are identical to the physical carrier designator. As the slide shows, the SEPT hierarchy multiplexes 32 E0 channels to create the signal that is carried within an E1 physical carrier. An E1 carrier provides a total transmission rate of 2.048 megabits per second. Similarly, the SEPT hierarchy specifies the following. 4 E1 signals are multiplexed to create the E2 signal used in E2 carriers. E2 carriers provide a total transmission rate of 8.448 megabits per second. 16 E1 signals are multiplexed to create the E3 signal used in E3 carriers. E3 carriers provide a total transmission rate of 34.368 megabits per second. 64 E1 signals are multiplexed to create the E4 signal used in E4 carriers. E4 carriers provide a total transmission rate of 139.264 megabits per second. 256 E1 signals are multiplexed together to create the E5 signal used in E5 carriers. E5 carriers provide a total transmission rate of 565.148 megabits per second. The Japanese digital signal hierarchy defines the signal multiplexing used to create the signals carried in each J carrier. Unlike DSX, Japanese DSDs are identical to the physical carrier designator. As the slide shows, the Japanese hierarchy multiplexes 24 J0 channels to create the J1 carrier signal that is carried within a J1 physical carrier. A J1 carrier provides a total transmission rate of 1.544 megabits per second. Similarly, the Japanese hierarchy specifies the following. 4 J1 signals are multiplexed to create the J2 signal used in J2 carriers. J2 carriers provide a total transmission rate of 6.312 megabits per second. 30 J1 signals are multiplexed to create the J3 signal used in J3 carriers. J3 carriers provide a total transmission rate of 32.064 megabits per second. 240 J1 signals are multiplexed to create the J4 signal used in J4 carriers. J4 carriers provide a total transmission rate of 397.200 megabits per second. Although the Japanese digital signal hierarchy has been defined, in practice, most PTTs in Japan use the T1 standard. The reasons for using the T1 standard will be discussed in Module 3. Encoding schemes define how digital signals are configured for transport through a physical transmission medium. Encoding schemes use electrical signals to represent the logical 0 and 1 bits in a data stream. The public carrier that provides the local loop service determines the encoding scheme for the WAN connection. All of the subscriber's equipment must be configured to use the public carrier's encoding scheme. 3 encoding schemes are widely used in T, E, and J carrier systems. Alternate mark inversion, or AMI, bipolar 8-0 substitution, or B8ZS, high-density bipolar of order 3, or HDB3. AMI uses alternating positive and negative voltage, referred to as alternating polarity or bipolarity, to represent logical 1s, and zero voltage to represent logical 0s. Because AMI uses zero voltage for logical 0, it can cause synchronization loss between peers at each end of a WAN connection when a data stream contains a long string of logical 0s. B8ZS is a modified version of AMI. B8ZS prevents the synchronization loss associated with AMI by limiting the number of consecutive zeros in a data stream to 8. When 8 zeros are detected, B8ZS replaces them with 2 successive logical 1s of the same polarity in a process referred to as a bipolar violation. B8ZS is the predominant encoding scheme used in T carrier systems. HDB3 is based on AMI and prevents synchronization loss in a manner similar to B8ZS. HDB3 limits the number of consecutive zeros in a data stream to 4, and it replaces them with 3 logical zeros and a violation bit with the same polarity as the last AMI logical 1 detected. HDB3 is the predominant encoding scheme used in E-carrier systems. Data link layer protocols are the third and final element of a basic WAN connection. Data link layer protocols are found at layer 2 of the OSI model. They enable flow control, synchronization, integrity checking, and validation for data streams passing between the physical layer and the network layer, layer 3 in the OSI model. Module 2 explains data link layer protocols in detail. In this module, you learned about the following: 3 basic elements of a WAN connection: physical transmission media, electrical signaling specifications, data link layer protocols, local loops and the public carrier networks that provide them. 3 types of circuits used to create a WAN connection: dedicated circuit, permanent virtual circuit, switched virtual circuit. Electrical specifications and related technologies. Digital signal hierarchies, DSX, SEPT digital signal hierarchy, and the Japanese digital signal hierarchy. Pulse code modulation, time division multiplexing.